Thank you, everyone, from the Defense Committee. We are now the five of us with Hubert, which is acting as a substitute. So I think we can start with the defense. And so, Christian, so you have 50 minutes to describe your thesis. Thank you very much.
Okay, thank you, Claudio. And thank you to the members of the jury for accepting to participate.
Can you hear, Christian?
Can you hear me? Okay. Thank you to the members of the jury for accepting to participate in my defense. So the results that I want to share with you concern the metastable behavior of one-dimensional diffusions. But before properly state the main results in my thesis, I would like to give some motivation and historical remarks. So metastability is a property exhibited by many physical systems. It is characterized by long periods of apparent stability, followed by an abrupt transition into a different state, which could be a stable state or another metastable state. Examples in nature include supercooled water, condensation of oversaturated water vapor, and magnetization. In the 80s, based on the Fredling and Benzel theory of large deviations, Cassandro, Galvez, Olivieri, and Bares proposed the first rigorous approach to deduce the metastable behavior of a Markov process. Later, in the 2000s, Bouvier, Gerhardt, and Klein developed a method based on potential theoretical techniques to derive sharp estimates for transition times between metastable wells. By the 2010, Beltran and Claudio proposed to characterize metastable Markov processes as those that can be effectively approximated by simpler Markov chains. This is called model reduction. More recently, in 2023, Landim, Seu, and Marcondes established a new characterization of metastability. They showed that the Markov process is metastable in the sense of model reduction if and only if the solutions to the associated resolvent equations are asymptotically constant within the metastable wells. This is the approach that we use in our work. Now, I would like to introduce the model. We work with a one-dimensional diffusion process, which is defined as the solution of this stochastic differential equation, where W, T, is the Brownian motion on the one-dimensional torus. The coefficients satisfy the following conditions. The drift B and the diffusion coefficient A are functions of class C2, A is strictly positive, and the set of zeros of the drift is finite and non-degenerate. The process is Markovian, and its generator is given by the following elliptic operator, whose domain is composed by functions of class C2 on the torus. So what happens with this process as epsilon goes to 0? To motivate this problem, let's fix an element in the torus and consider the following ODE. A classical argument by Fredling and Benzel shows that if we fix a window of time, the diffusion, conditional on starting at the initial condition of this ODE, converges in probability to the solution of this ODE inside this window of time as epsilon goes to 0. This means that if we fix a stable equilibrium point of the ODE, the diffusion condition on starting at its domain of attraction for small epsilon seems to get trapped in this domain of attraction. Nonetheless, for each positive epsilon, the diffusion is irreducible. So what is going on? Let's consider, for instance, the case of a double well potential. And for this situation, the Eyring-Kramer's formula provides the mean transition from one minimum to another. Here in red, we have a term that explains the previous apparent paradox. If we fix a window of time and then send epsilon to 0, we don't see this transition from one minima to another, because this transition occurs at a time of order exponential in epsilon. But what if we analyze the diffusion rescaled by a time scale that encodes this barrier? In this case, we expect to see that the diffusion rescaled for epsilon small should be well approximated by a Markov chain that jumps among these minima. So we are interested in the symptotics of the diffusion at every non-trivial timescale. A second object that we study in the thesis concerns the solution of certain parabolic PDEs. So let's fix a continuous function on the torus and consider the following initial value problem. It is well known that this solution has a stochastic representation given in terms of the diffusion. Because of this formula, it makes sense to study the asymptotics of the solution of this parabolic PDE via the metastable behavior of the diffusion. So we are also interested in the asymptotics of this solution at every non-trivial timescale. A third object that we study concerns the rate functional of the associated to the large deviation behavior of the occupation measure of the diffusion. Let's denote by this expression the set of probability measures on the torus equipped with a weak topology. Let L epsilon t be the empirical measure of the diffusion. This is a random element in this space. And for each measurable set on the torus, it provides the proportion of time that the diffusion spends on that set during an interval from 0 to t. Let's denote by pi epsilon the stationary state of the diffusion. Since the diffusion is irreducible by the ergodic theorem, the empirical measure will converge in probability to the stationary state as t goes to infinity. In 75, Donsker and Baradan showed the associated large deviation principle, which informally says the following. Here denote by px epsilon the distribution of the diffusion condition on starting at x. So for every measure in this space, the probability of having the empirical measure close to this measure mu behaves as t goes to infinity like an exponential of minus t times a functional applied to mu, where this functional is given by the following variational problem, where here d plus L epsilon is the set of strictly positive functions that belong to the domain of the generator of the diffusion. Now this setting is for a fixed epsilon. So what happens with the rate function when we send epsilon to 0? In order to study the convergence of this functional or the asymptotics of this functional, we use the notion of gamma-convergence. So to define it, let's fix a Polish space X and a sequence of functionals defined on that space. We say that this sequence of functionals un gamma converges to a functional u if the following two conditions are met. First, if the functional u is a gamma limit for the sequence un. This means that for every x in the space and each sequence converging to x in the topology of this space, the limit of un applied to xn will be lower bounded by our limiting functional u applied to x. The second condition tells us that the functional u has to be also a gamma lim sup for the sequence un. This means that for each x in the space, there exists a sequence xn converging to x such that the lim sup of the sequence of functionals applied to xn is upper bounded by ux. Since the generator of the rescaled diffusion is given by this expression, then by the definition of the rate functional, the associated rate function will be given by this expression here. Just a bit of notation, for two positive monotone sequences, alpha epsilon and beta epsilon, such that beta epsilon is much bigger than alpha epsilon in this sense, we are going to use this notation here. So we are interested in the asymptotics of the rate functional rescaled at every non-trivial timescale. Some previous works regarding these problems are the following. Regarding the model reduction, there are applications of this characterization and metastability in models like the reversible zero-range process, the reversible and non-reversible inclusion process, random walks in potential fields, among other models in statistical mechanics. Regarding the resolvent approach, it has been applied to models like non-reversible diffusions with a constant diffusion coefficient and an associated Gibbs measure, and to the critical reversible zero-range process. With respect to the asymptotics of the solution of the previous parabolic differential equations, there are works tackling asymptotics for intermediate timescales using the large-deviation theory by Fredling and Wenzel. And also, there are the works by Landim, Le, and Seo in 23 and 24, where they study the asymptotics of dissolution for the case where the generator, where the operator is given by a generator of a multidimensional diffusion that has a Gibbs measure as a stationary state and a constant diffusion coefficient. Regarding the asymptotics of the rate functional, a connection between the asymptotic behavior of the rate functional and metastability for the case of metastable Markov processes on finite-state spaces has been established in a series of works by Landim, Isturini-Sau, Bertrini, Gabrieli, and Landim. And also computations of the asymptotics of the rate functions for from certain specific models like the zero-range process appear in a work by Choi in 24. And the computation of the asymptotics of this rate function for multidimensional reversible diffusions under the assumption that all of the local minima has distinct depth has also been analyzed in a work by Di Gesù and Mariani. Also, a couple of months ago, it was submitted a paper where that tackled the asymptotics of the rate function for multidimensional reversible diffusion without this assumption of having all of the local minima with distinct depth. Now I would like to give some remarks about the assumptions that we suppose for the work. If the integral of the quotient B over A over the torus vanishes, then in this situation the stationary state of the diffusion will be given by a Gibbs measure, where here C epsilon is a normalization factor. In this context, the process will be reversible with respect to this measure. Moreover, Donskar-Baranen proved that for every measure mu that is absolutely continuous with respect to this Gibbs measure, the rate functional will satisfy this formula, where f mu is the Radon-Nikodym derivative of mu with respect to the stationary state. In contrast, if the integral does not vanish, the process is not reversible. The stationary state is not a Gibbs measure, and the rate functional does not satisfy the previous formula. We assume that this integral is greater or equal than 0. Therefore, our analysis includes the case where the process is non-reversible and its stationary state is not given by a Gibbs measure. We also work with a non-constant diffusion coefficient, and we do not assume the local minima to satisfy the condition of having all of them distinct depth. Now, in the remaining of my presentation, I will structure in 3 parts, and each one of those will be related to one particular result of the thesis. The first one, I will introduce our result regarding metastability, regarding the asymptotics of the diffusion. Then the result regarding the asymptotics of the solution of the parabolic PDE generated by the generator of the diffusion. And finally, the results regarding the asymptotics of the rate function. So to fully describe the asymptotics of the diffusion at every non-trivial timescale, we need to define the timescales at which we see escapes from stable equilibrium points. And we also have to define the Markov chains that will describe these metastable transitions. To do this, we need information about how is it that we transition from one minima to another. To extract this information, we use this potential to compute the height of the barriers that separates local minima. Let's recall that S might not be defined on the torus because the integral from 0 to 1 might not vanish, so S might not be necessarily periodic. So what we are going to do, we are going to describe the full structure on R, where S is well defined. And we can do this because the information that we actually need is merely local. We need information about how is it that we transition from one minima to another. So the results on metastability and the asymptotics of the PDEs are going to be presented in this context on a real line. The same proofs and results will apply to the torus. And after having this metastable structure and the results regarding the asymptotic behavior of the diffusion on R, we're going to project this situation to the torus in order to state the results regarding the asymptotics of the rate functional. So we are going to consider now a diffusion on R, where Wt is the predominant motion on the line, and A and B are going to be the same functions as above, but understood as periodic functions on R. Therefore, in this situation, the stable equilibrium points or local minima of the potential at the unstable equilibrium points or local maxima of the potential are going to be infinite, although inside each interval of size 1, they're going to be finite. We are denoting by n the number of local minima and local maxima inside each interval of size 1. And we are going to order these elements in this way, so that sigma 0 is going to be the rightmost local maxima, the leftmost local maxima to the right of 0, and mn minus 1, the rightmost local minima to the left of 1. Because of the periodicity of the coefficients, the local minima and the local maxima will be periodic in this sense. I would like to describe now the first order metastable structure. So for each local minima, we are going to define the escape barrier to the left as the difference of the potential applied to the nearmost local maxima to the left of mk, and the potential applied to mk. And in a similar way, we are going to define the barrier to the left. H1 is the minimum over all of the escaping barriers. Now, since the coefficients are periodic, the differences here are going to be periodic as well. Therefore, we can take the minima here because we are considering a finite number of different values. And since each of these barriers is strictly positive, H1 is going to be strictly positive as well. The first metastable scale will be defined as the exponential of H1 over epsilon. And the first Markov chain will be defined through these jump rates. For instance, a jump rate from nk to mk plus 1 will be encoding some weight put on the local minima mk at which we are, and this weight depends on the coefficients of the generator, and some weight on the maxima that is between these two local minima. And this weight also depends only on the coefficients. Here, this indicator tells us that we are going to have a jump provided that the barrier that separates these two local minima is not greater than the minimal barrier H1. We are going to denote the chain defined through these jump rates by this symbol and its associated generator by this symbol here. Since the jump rates depend only on the coefficients, they are going to be periodic. So the chain will be periodic as well. So we may just focus actually on inside intervals of size 1. If we have only one closely reducible class inside an interval of size 1, then this chain will capture all of the metastable transitions of the diffusion x epsilon. On the other hand, if this chain has two or more closely reducible classes inside an interval of size 1, this means that we will have two subsets disjoint, each of them having local minima, such that the rescale diffusion at the exponential of h1 over epsilon will be trapped in either, if we condition that rescale diffusion to start in either of these two sets, it will get trapped. For this situation, what we can do is consider the smallest barrier separating recurrent classes of this chain and define a new timescale that captures the heights of this barrier. And for this new regime, we may define a new Markov chain that has the closely reducible classes of X as its state space. In general, each metastable timescale and each Markov chain will be defined through a recursion, through a recursive procedure. And here we have a picture that illustrates this recursive procedure. In green, H1 is the minimal barrier separating local minima. For instance, the chain associated to this barrier, X1, it can jump from M0 to M1 and from M1 to M0, but it cannot jump from these 2 points outside, and it gets trapped in any of the other points. Therefore, this chain has more than one closely reducible class, so we can consider the minimal barrier separating the closely reducible classes of this chain and build a new level, X2. Now, at this new level, what we are going to have is that this closely reducible class composed by these two local minima will be now one state for this new chain. This new chain can escape from this set of these two local minima, but it will get trapped in the others. So we may consider also another barrier separating the recurrent classes of X2 and build a new layer. At level 3, we lose these two local minima here. And this happens because at this level 3, we are encoding the asymptotics of the diffusion rescaled by the exponential of this barrier here over epsilon. At that speed, the diffusion will not spend much time in this set here. So it will escape pretty fast from that set. Now at level 4, we can see the following. Here we have one state that is composed by the recurrent class of the previous layer, and we have a jump from this state to this state here, because the barrier that separates these two states is exactly the minimal barrier at level 4. And the jump from this state to this one should encode some weights regarding the local minima that belong to that state and the maxima that separates these two states. Moreover, the potential restricted to any of the states builded in this recursion is going to be constant. In other words, the minima belonging to the same state are going to have the same depth. Finally, we are building each chain in a way such that each chain is non-degenerate. So each chain will jump from at least one state. Therefore, inside an interval of size 1, the number of states will be strictly greater than the number of recurrent classes. In consequence, the recursion has to stop eventually. Well, as I said, the chains of higher orders will jump from between subsets of local minima, and they should encode weights regarding the minima belonging to these subsets and the maxima separating these subsets. Each chain of higher order level will be denoted by this, and the associated generator by this. In general, the full metastable structure is built through a recursion that will produce a finite number Q of layers, composed by a partition of the stable equilibrium points, a minimal barrier, a timescale that depends on this minimal barrier, and a Markov chain that jumps among subsets of stable equilibrium points. Moreover, the minimal barriers at each level are hierarchically ordered in this sense, and the metastable timescales, because of the way they are defined, are going to be also hierarchically ordered in this sense. As I said, each new chain jump has as its state space the closely reducible classes of the previous one. And we are going to prove actually this, that at each level the diffusion rescaled by the associated timescale should be well approximated by the Markov chain at that level produced by the recursion. Now I would like to be more precise and state the results regarding what do we mean by this. These two results concern the characterization of metastability according to model reduction and the characterization according to the resolvent condition to metastability. I will present first the characterization regarding model reduction, and to do this I first need some preliminary definitions. The first one is the one of metastable wells, which are the sets at which the diffusion spends most of its time. So here in this picture we have in red, the minimal barrier separating local minima. Here we have in brown a height that is strictly smaller than this minimal barrier. And with respect to each local minima, we are going to define an associated metastable well that is going to be the connected open set that contains that local minima and contains also all of the points that are below this height. For higher order levels, we're going to define higher order metastable wells as the union of the wells associated to the minima belonging to the state here that generates this higher order metastable well. We are going to denote by EP the union of metastable wells at order P, and by delta P the complement of this set. The rescale diffusion by a time scale of level P will be denoted like this, adding this extra P. Now we are going to define a couple of random times. For instance, this one can be understood as the time that inside an interval from 0 to t, the time that the diffusion rescaled at time scale at level P is spent inside metastable wells of level P. Here we have the general inverse of this random time, and we can understood this random time as follows. For each fixed trajectory, this is going to be discontinuous. It will increase continuously while this trajectory is inside the metastable wells, and then as soon as this trajectory escapes, it will jump to the next time at which it reaches another metastable well. It turns out that this random time is a stopping time. The trace process will be defined as the rescale diffusion with a change of time given by the previous random time. Therefore, the trace process behaves like a diffusion, although it has as its state space the union of metastable wells at level P. Since this is a stopping time, then the trace process will be a Markov process. Finally, the order process will be defined as the projection of the trace over the state space associated to the reduced Markov chain at level P. For instance, since each higher order metastable well is related to a state by the definition that I gave, the projection of the trace will give the associated state whenever the trace is in the associated higher order metastable well. So the result regarding model reduction tells us the following. First, let's denote by this expression the probability, the law of the trace process. Here, by this Q epsilon t, the law of the order process, which is the projection of the trace. And here, by QP, without the epsilon, without the t, the law of the reduced Markov chain at level P. So the result regarding model reduction tells us that the order process will converge, that the law of the order process converges weakly to the law of the reduced Markov chain. So in this sense, the reduced Markov chain produced by this recursive construction encodes the dynamics among the wells. On the other hand, this second statement tells us that the time that the rescale diffusion spends outside the metastable wells during an interval from 0 to t in expectation is trivial as epsilon goes to 0. So this means that actually the most important thing is occurring inside the metastable wells. So in this sense, this reduced Markov chain is encoding the asymptotic behavior of the rescale diffusion. Now I would like to introduce the result regarding the resolvent condition to metastability. Let's fix a layer of the one produced by the recursive construction, and let's fix also a bounded function defined on the state space of the associated Markov chain. We're going to lift this function to R like a linear combination of indicators over metastable wells at level P. Now, let's consider the solution of this resolvent equation, where here we have the generator of the rescaled diffusion at level P. So the result, what tells us is that uniformly inside the metastable wells, the solution to the resolvent equation associated to the generator of the diffusion will converge as epsilon goes to 0 to a solution of the resolvent equation associated to the generator of the reduced Markov chain. So this means that the solution of this resolvent equation is going to be asymptotically constant among the metastable wells. Now, Landim, Marcon, de Sanseo, they showed that these two properties, the model reduction and the resolvent condition, are equivalent for the case of finite-state metastable Markov chains. Then Le and Seo showed that if you manage to prove the resolvent condition for diffusions, then you get the model reduction. So we prove model reduction by proving the resolvent condition and applying the result by Le and Seo. Moreover, the resolvent condition is useful for proving the asymptotics of the rate functional. On the other hand, the model reduction characterization of metastability is useful for tackling the asymptotics of the solution of the parabolic PDEs. Now, I would like to turn to the second result of the thesis, which concerns the asymptotics of the solution of parabolic PDEs. First, some notation. Let's denote by tau A the heating time of this to the set A of from the diffusion. Let MP be the set of local minima at level P. By that I mean the union of all of the states at level P. And let's define this probability on the state space of the reduced Markov chain at level P, which can be understood as follows. For each x, this probability for each x, this is giving us the probability that the diffusion conditional on starting at x, when hitting the local minima at level P, it does that by hitting first this particular state. This result is the most important tool for proving the asymptotics of the solution of a parabolic PDEs. It can be understood as a convergence of the finite dimensional distributions of the here P epsilon is the distribution of the diffusion of the rescaled diffusion at level P. So this can be understood as the convergence of the distribution of the rescaled diffusion over the metastable wells to the finite dimensional distributions of the reduced Markov chain. Now, the way that we get to this result is via the model reduction result, and we use a method developed by Landim, Loulakis, and Murray that actually consists in showing that from model reduction, from the convergence of the order process, you can get to the convergence of the finite dimensional distributions of the trace, and then get here by showing that from getting from the trace to the finite dimensional distributions of the rescaled diffusion, the price that you pay is going to be asymptotically negligible. This result here tackles the asymptotics of the diffusion among the higher order metastable wells. But recall that each higher order metastable wells is composed by the union of the metastable wells associated to the minima that belong to the associated state. This second result gives us the asymptotics of the probability of having the diffusion in a particular metastable well of lower order. So let's fix a level P let's fix a well of order P associated to a particular state MPJ. Let's fix a time T. Let's fix also a different state with index K and a minima in this other state. So this result tells us the following. The probability of having the rescale diffusion that starts in this metastable well associated to the state of index J at time T in this well associated to this minima that belongs to this state of index K, as epsilon goes to 0, looks like this expression over here. Now, what this expression is telling us? First, this one is the probability of having the reduced chain conditional on starting on this state, which is the one associated to this well, at time t in this well here. And now this other expression, how is it that we can understand it? Well, let's recall that this state is a recurrent class for the Markov chain at the previous level. Moreover, the reflected chain of the previous level over this recurrent class will have an invariant measure that satisfies this formula. Where these two are the weights on the states that I defined before and that appear in the definition of the rate of the jump rates. So how is it that this is appearing? Well, the states of this level that belong here are separated by barriers that are smaller than the barrier associated to the level P associated to this timescale. Therefore, when the diffusion reaches this state, it is reaching it in this timescale. So the diffusion will move pretty fast among all of the states of the lower level that belong to this recurrent class. So it will equilibrate there. And the time that it spends on each of these lower level states will be given by the stationary state. And proceeding like this, inductively, we are going to get to this expression here that can be understood as the proportion of time that the diffusion spends near this local minima when it reaches this state of level P. Now I can properly state the main result regarding the asymptotics of the PD. Let's denote by PTP the transition probability of the reduced Markov chain at level P. So let's fix an initial condition given by a bounded and continuous function U0. The first item in the theorem provides the asymptotics of the solution rescaled by a metastable timescale. So for a fixed t, here the asymptotics will be given by this expression. This expression is a combination of the initial condition applied to a subset of local minima at level P. The weights in this combination encode the metastable dynamics of the rescaled diffusion at level P. So how is it that we can understand better what is going on here? First, let's recall that the stochastic representation of the solution of the parabolic differential equation. So what is going on here is that the diffusion rescale at time scale at level P is reaching pretty fast local minima at level P. And here we have the probability that it reaches a particular state at this level. Then the diffusion will reach at time t a particular higher order metastable well, associated, for instance, to the stable state associated to the higher order state with index L. Now, inside that higher order metastable well, the diffusion will spend some time among the lower order metastable wells belonging to that higher order metastable well. And the probability of having the diffusion in each of these lower order metastable well was given by the previous lemma, and is actually this expression that we have here. Moreover, if we recall the definition of the metastable wells that was given through a particular height, and moreover, we also recall that the jump rates are periodic. Therefore, at time t, we cannot be too far from the state mpk. We can just fix an interval sufficiently big so that the probability of having the reduced chain outside of that interval will be very small. Now, on that interval, the function u0 is uniformly continuous. So if we reduce the height now, when the diffusion is now in this way with a smaller height, we can do a replacement with the value at that particular minima here, with a cost that is going to be negligible. So this is how we can actually understand what is going on here. The second item provides the asymptotics for the case at which we are regarding the solution at an intermediate timescale, in between metastable timescales. Notice that here we lose the dependence on the time. We lose the dependence on the time principally because, first, this timescale is bigger than the timescale at level P. Therefore, the diffusion at this timescale will escape pretty fast from any transient state of level P or previous levels. So it will reach very fast a recurrent class of level P, which is a state of level P plus 1. But since this scale is smaller than the one at level P plus 1, the diffusion at this scale cannot escape from the states at level P plus 1. Therefore, it remains trapped here. And in this state, it equilibrates. And that is given by this expression here. The final result, the final item, provides asymptotics at timescales given at timescales that are smaller than the smallest timescale at which we see escape from local minima. The last result concerns the asymptotics of the rate functional.
You have 5 minutes, Grisha, so 6 if you want, but not.
Okay. So the last result concerns the asymptotics of the rate functional. Let's recall the definition of the rate functional and the definition of the gamma-lim inf and of the gamma-lim sup. If we want to prove a gamma-lim inf, it's actually enough to find a good test function in the domain of the generator, because that will provide a lower bound, which is actually what we want here. So for the gamma-lim inf, we actually don't need to provide a good estimator for the variational problem. On the other hand, for the gamma-lim sup, since the inequality is in the other direction, we do actually need to estimate the solution of this variational problem for the recovery sequence that is going to give us the desired upper bound. We have such an estimator via this lemma, which gives us a formula for the rate function for the case where we apply it to a measure whose density is of class C2 and strictly positive. And the recovery sequences that we actually use in each of the regimes has densities that are of class C2, but which vanishes on sets of Lebesgue measure which vanishes on sets of which has a strictly positive Lebesgue measure. But just by perturbing these densities, we can actually manage to use this formula to get an estimator using the lower semi-continuity of the rate function. The first regime concerns the asymptotics at which the diffusion seems to get trapped at every critical point. And the associated functional limit is given by this expression here, where mu is the Radon-Nikodym derivative of the absolute part of the measure mu. In the case where we have, and here B is the integral of the quotient B over A over the torus. So if we are in the setting of a reversible diffusion, we lose this term and only get this one. The result regarding this regime tells us that at the speed epsilon, the rate functional converges to this functional. And moreover, epsilon provides the smallest speed at which we see a non-trivial behavior in the limit. The second regime corresponds to the timescale at which the diffusion process escapes from the local maxima. And here we have the limiting functional. This limiting functional is finite when we apply it to a measure that is a convex combination of Dirac's applied to the critical points. If in the support of that measure we have unstable equilibrium points, it will be positive. Otherwise, it will be 0. We know that this is exactly the second regime because the set of measures at which this functional is finite is exactly the same at which the previous functional vanishes. And the result associated to this regime is the following. The rate functional at natural speed gamma converges to this functional. Now, with respect to the higher order regimes, we are going to use the metastable structure to obtain the chains. We are going to use the metastable structure to get the proper speeds at which we see a non-trivial behavior in the limit, first. And second, the limiting functionals will be defined as some lifting of the rate functional associated to the reduced Markov chain that encodes the dynamics of the rescaled diffusions. So, by the periodicity of the rates and the periodicity of the states, we can just project the previous structure to the torus. And define now on the torus a Markov chain and a rate function associated to the large deviation behavior of the occupation measure of this chain. As I said, we define each limiting functional as a sort of lifting of this previous rate functional. At each level, the functional will be finite provided that the measure is a convex combination of these measures defined here. And it's going to give us as a value the rate functional applied to the measure that is given the weights in this convex combination. This measure here, because of what I just explained in the previous result, can be understood as, well, first, it has its support inside each of the states at level P, and second, if we apply it to a local minima belonging to the state MPK, it will provide the proportion of time that the diffusion spends near the local minima M when it reaches the state MPK. And the result regarding the asymptotics of the rate functional says the following. Let's denote by theta minus 1 the speed provided by epsilon, by theta 0 the natural speed. And so the speeds, these two speeds and the metastable speeds and the functional that I just defined will satisfy the following statements. First, as I said, the speed epsilon provides the smallest one at which we see a non-trivial behavior in the limit. Second, I also mentioned this, these speeds are hierarchically ordered. Third, each functional here is going to be the gamma limit of the sequence of rate functionals rescaled by the associated timescale, which for p greater or equal than 1 will be the speeds given by the metastable timescales. And finally, each of these functionals applied to mu are going to be finite if and only if the functional at the previous level vanishes at mu. So these three last conditions tell us that at intermediate timescales we are going to have trivial behavior in the limit. Some references here, and so this is all. Thank you.
Thank you very much, Christian. So now we will open for questions. So let's start from the farthest one, Ivailo. If you have any question, you please ask them now.
Sure. Okay. Can you hear me, by the way?
Yes, perfectly.
Okay. So let me just start by thanking Christian for the thesis, which I understood surprisingly much. I did not expect that. So let me start with a naive one. So in chapter 2 and also towards the beginning of your presentation, the starting point disappeared. I think this was already at the level of Tosker and Varadhan's result. Can you comment on this?
Sorry, could you repeat the starting point?
Yeah. So the starting point itself disappeared at the very beginning.
The rate function doesn't depend on the starting point.
Yes.
Ah.
So can you explain this anyway?
Well, what's going on, Ivailo, is that these are the large deviations as t goes to infinity, right?
Yes.
So if you start from x, you can, at finite cost, go from any x to any y for a finite cost. But since you're sending t to infinity, this finite cost that you pay to go from x to y will disappear asymptotically. So this is why you don't see the initial state.
Sure. Okay. Thanks. I can move on to a second naive question. Then I will ask maybe a less silly one. So in the first chapter, you have the case where your potential is not periodic. So S of 0 is not equal to S of 1. And you're saying that you don't have an explicit formula for the stationary state. Why is that?
In the case of R, or in the case of
On the torus
we have a
S1 is different from S0.
Yeah, but we have an explicit formula for the torus that is provided by Fayonnato and Gabriele. But so it's easy to compute it in the case of reversible. In the reversible case, it's just the Gibbs measure provided by the potential. But now in R, you have it if you localize. I mean, inside each compact set, if you consider the reflected diffusion there, then you could have an invariant measure provided by the Gibbs measure over there. But in all of this case, no.
Oh, this makes sense. Okay. And the last one I have is a bit more general. So how does this resolvent approach compare to the previous ones that you mentioned at the beginning?
So it depends on what you want to prove, I think. First, for instance, for proving the asymptotic behavior of the rate functional, the resolvent approach gives you a way to control solutions of these resolvent equations, and you can use them to build the test functions that you need to prove, for example, the gamma lim inf. So it gives you that control. That's one thing. Second, with respect to model reduction, for instance, I think it's much easier to prove this convergence of the solutions, because in the case of the resolvent equation, your solutions are bounded. It's not that difficult. Now, with respect to the others, I think it depends on the problem. For showing the asymptotics of the rate functionals, I don't know how to use the others approach actually. But
if I may add, so all methods existing depend on the explicit knowledge of a stationary state, because you rely on explicit computations. Okay? So what we are trying to do is to develop tools which do not require the knowledge of the explicit. So this is one. So if you have, you can always write your resolvent equation and try to prove this is a differential PDE problem and try to show that the solution is asymptotically constant close to the on the wells, on the bottom of the wells. So maybe one can find an analytical approach in order to prove that, which do not rely on the existence of stationary state. And the same thing for the large deviations. You can always write the large deviation rate function, doesn't require the explicit knowledge of your stationary state. And maybe you can try to prove with analytical methods that these rate functions converge. And then you will recover the metastable behavior of your process. So these are tools that have been developed to avoid using these explicit computations.
I see. Okay, thanks. Well, that's good for me.
Well, thank you, Ivailo. So let's go to Giulio.
Right.
We can hear you, Giulio.
Just a second, please.
Yes, now it's perfect.
Yeah?
Yeah.
Can you hear me?
Yeah, now we can.
Okay, so first of all, thank you very much for inviting me. And it's been a pleasure to read the thesis, the 2 chapters. And I have one general comment which I would like to understand a bit better. It's not completely tied to the 1st and 2nd chapter, but is somehow related to the old work, and is this resolvent approach to metastability. And in particular, I was quite curious. I didn't know anything about it, and it seems to be quite recent work. And if I understood correctly, this resolvent approach relates metastability to model reduction in a certain sense. And but my question is quite specific about the resolvent equation itself, which depends on an extra parameter lambda, which is a positive real number. And the question I had, which I could not answer myself, is the following: why to consider the resolvent equation and not directly the Poisson equation, which would correspond to setting lambda to 0?
yeah. Okay, so in the case of the resolvent equation, your solution is going to be bounded. And so to prove that your solution, for instance, in this case is constant asymptotically, having that is actually very helpful. I think yes. And if you have the Poisson equation, and you manage to prove this this convergence, yeah, via the martingale problem, you should have also a characterization of the limit via that direction. But it seems that it's easier to deal with the resolvent equation, actually, than the Poisson, for proving exactly what you need in order to be able to characterize the limit.
I see. But do you think it will still be true that the functions are constant over the wells for the solution of the Laplace equation, or the Poisson equation?
A priori, I'm not quite sure. I know that this is the approach that Claudio and Seo use to characterize the limit in a work also related to diffusions, to non-reversible diffusions. But in having more in a more general setting, I'm not quite sure. I'm not quite sure.
So if I may add an historical point, actually the method was introduced with the Poisson equation by O and Reza-Kalou. And so they proved that for a certain zero-inch model, that the solution of the Poisson equation was constant on the wells. But as Christian said, I mean, solutions of resonance equations are much more regular. They always exist, which is not the case for Poisson equations. So this simplifies a lot, though it gives the same results.
I see. Well, thank you. Another question I have is more a curiosity and is related to chapter 1. Well, chapter 2 of your thesis, but the first, let's say the first article. And you mentioned the result in the presentation, but very briefly. And is the result which concerned the time scale, which is lower than the first time scale, which is related to the shallowest well. And basically, if I understood correctly, it says that when you start from a local maxima, then you drop to one of the minima, one of the right, one of the left, of course, symmetrically, so with probability 1/2. But I could not really get why this slower time scale should not be too slow. In particular, it should be bigger than 1/epsilon. So it should go to infinity, but cannot go slower than 1/epsilon. So I was wondering whether this is just a technical question, or is there any physical intuition why it should not be true for even slower rate?
So first, the diffusion don't need a scale that has to be of order 1/epsilon to escape the local maxima. It can escape at a smaller scale. And actually, the way that we prove that we estimate the heating times in the section 4, we can use it to show that the diffusion can escape from local maxima at an order. I think you can go until log of square root of epsilon 1. I mean, log of epsilon of 1/epsilon over square root of epsilon, and maybe a little bit more. I know that there is a work, I was talking with Claudio recently, by Kiefer, when he shows that the minimal scale that you need to escape is of an order logarithmic. It's of a logarithmic order. But yes, I mean, it's not sharp actually, that part there in the thesis. I mean, that particular scale at which we put the escape of the local maxima is not sharp.
Okay. Maybe just one more question. Well, it's more of a comment I don't know if you really changed then your thesis, but in the presentation, I guess you present the result for the representation of the level 2 rate function in a different way. And actually, that was my sort of question, because I could not really understand if while in the third chapter you present the result for the first time scale separately from the second, the third, and the further ones. I understand that when you look at the first time scale, you get that the level 0 is concentrated on this convex combination of Dirac on the stable points, and but for the other one, you have to introduce a particular measure which depends on the order. But as far as I understood, this measure in the first level really reduces to the Dirac measure. So in a certain sense, in the version I have, you have a proposition, and then you have the main theorem, which actually the main theorem does not consider the first level, and the proposition does. But according to what I understood from the definition of the things, everything could be included in the theorem, even the case for the first time scale, namely p equal to 1.
Yes.
I saw that you presented the work in this way, so I was wondering whether this is correct what I'm saying, and whether you have already changed it in the final version of your thesis.
No, I didn't change it in the final version of the thesis. I changed it in the presentation because of the time, and I thought that it was better to put all of the results regarding the rate function at the end. And since I had already introduced the metastable structure, I could give all of the results together.
I see. Well, then I guess I stop here. And many congratulations, because as far as I see, you really show a very good understanding also of the physical phenomena behind. So many congratulations, Christian.
Thanks.
Thank you, Giulio. So let's continue with Milton.
Well, congratulations, Christian. It's a very nice work what you have done in your PhD thesis. So I have to say that I cannot criticize a lot the mathematics, because it's I think it's very nice. I can criticize a little bit the writing style, because for the reader it's very difficult to follow when you use all these strange alphabets in your text. I mean, it's you may have noticed that when you wrote at the blackboard, you didn't distinguish between fractured P and normal P. Because, of course, when you write it on the blackboard, you cannot do it.
No.
Of course, that's the case for me, too. I mean, I actually printed, you see, the thesis, and I have a lot of trouble trying to distinguish whether an index, for example, as Windex, is a normal P, a fractured P, or etc. And I didn't see any logic about how these letters were decided. And there are some nice pictures, but they are a little bit scarce and put it a little bit far away. You see, there is something like 20 pages of definitions until the mathematics really starts. So it's a little bit demanding for the reader. I mean, if I were not a jury of the thesis, probably I would have given up way earlier reading this text, and that's a pity, because the work is very good. So it looks like you were writing the thesis for Claudio, not for us. And that's a problem because you have really good material, mathematically speaking, and it's going to be your letter of presentation for a while. Okay, so people, when you apply for postdocs, for positions, for conferences, etc., they will look at your at your paper, your preprint, your thesis, and they probably not be able to understand the depth and the quality of your work because it's hidden in page 20, 21, 23 of the text, no? So this is something that should be addressed. Maybe now it's too late to address it for the thesis, but maybe for the preprints it's still you're still on time to do that. So the first result, no, which is 66 pages long. So the first two chapters of the thesis, which contains basically the first result, no, it's 66 pages long. It's very long, which means that you could have taken the liberty, no, to make the decision to include the explanations. So there are definition. Why are these definitions done? I don't know. I will know about it 25 pages later. I used to say that when you do a definition, you have to do it twice. Okay, once it has to be a mathematically rigorous definition, and a second one has to be an understandable definition for the reader. Sometimes these two definitions are the same, but sometimes they are not the same. Okay, and this is especially true for all this story about the classes, no, this sort of tree structure. In some point of the thesis, you mentioned, oh, there is a tree structure. So what is the tree? Okay, so it would be nice. It would have been nice to see actually the tree. No, okay, there is this picture that you put on your presentation. No, in your presentation, of course, you had the chance to explain very well how this inductive procedure works on an example. No, but this is not on the text, and people are not going to look at your presentation, no, your thesis defense are going to going to the text, no. So in figure 1, you have this figure, and there is this tree downstairs, no, the sort of tree-like structure, but in a very long paper, we are allowed to include a lot of explanation, a lot of colloquial words about what we are doing. Okay, because the text is already long. So sometimes people say, okay, I'm not going to explain things because it's going to make the paper or the thesis or the chapter way longer. And but if the text is already very long, you can take your time to explain what you're doing. And it's important because people are not going to read 20 pages of definitions until they start to find the mathematics behind it. Okay, so this is something I wanted to say about the mathematics itself. I don't really have a lot of comments. There is only one point on which I was a little bit curious. You were not very specific, which is in corollary 221. So there are these square root of 2 pi factors popping out in various places on the computations of the rates, and of course this square root of 2 pi factors comes from the Laplace method. Okay, so this is mentioned in very quickly in Corollary 221. You say something, you just use the second order Taylor expansion to conclude. This thing has a name, it's called the Laplace method, and it's a delicate thing. Okay, so it's not yes, it's the Laplace method, because in the Laplace method you have an integral, right, that is approximated by a Gaussian, and one has to take the time to verify that the error is actually integrable. Okay, because when you use, for example, you use a lot of this notation O epsilon of 1, which is not very, I think it's not explained in anywhere where it is, but sometimes this O epsilon of 1, it's O epsilon of 1 in this at this when you compute this integral, sometimes it's a uniform bound of O epsilon of 1, but sometimes it's an integrable bound of O epsilon of 1. Okay, so this is something that has to be very clear everywhere. Okay, because if you want to use the O epsilon notation, you have to be very specific about it. Okay, and so when this is general things, I mean that it's about writing, no? That it's for example. Yeah, I mean, I would have liked to have all these more explanations. I mean, to explain better what are you doing in each step. I mean, it's for example, something which is more or less clear is that so that the proof for the first level and the proof for the other levels, no, is basically the same.
Mm-hmm.
So there are just a few differences, but it would be nice to warn the reader about it. No, so I mean, if you look at the beginning of section 2.5, you say the proof is similar to the one presented in the previous section with one major difference. It would be nice that at each step of this proof, you warn the reader. This proof is just a repetition of what we did in 2.4. Because I mean, for example, when you start to talk about local ergodicity, it's basically it's almost verbatim to the proof, and then and the same with all the other subsections. It's a little bit disappointing that you don't warn the reader about all those things. No? So in lemma 2.33, for example, you say, okay, the proof of this lemma plus the result is omitted because it's very similar to the proof of the lemma 2.26. But the whole section is actually very similar. Section 2.5 is actually similar to the section 2.4. So why you can omit the proof of lemma 2.33 and you cannot omit the whole section? This is not clear from the text.
Mm-hmm.
You see? And well, there is a little bit of inconsistency on the notations. I mean, at the beginning of this paper, you were very careful about defining everything from the beginning, and only once everything is well defined, you start to do your computations. But then in the last parts of the paper, it's the opposite. It's the other way around. So, for example, in lemma 2.34, you use some notation omega something that is only defined in lemma 2.35 after the lemma, and one has to understand that the definition of this thing is given afterwards, from out of nowhere. So that these are things that I think especially when you have a very long paper with a lot of definitions, you have to be very precise. If the definition has not been done recently in the paper, you have to put a marker. Okay, say, okay, this concept here was defined in equation 2 point something. And the same is true for concepts that you are going to define afterwards. It could be that for the flowing of the thing, it's a good idea to do that. But then you have to warn the reader one more time about what you're doing. Okay. So yeah, as I was saying, so this is I think that mathematically the work is very good. It's a very solid piece of work. But you have to make it the text more palatable to the reader, because you are losing here a very good opportunity to show how good is your actual work. Okay, so I didn't read with a lot of care the section 3, because it's as you were saying at the beginning, it's a work in progress. But I think that the same basically the same comments apply for section 3.3. Okay, so I think that's what I wanted to say. It's I don't really have a lot of questions about mathematics. Actually, I think it's a very sound result, very interesting, and congratulations one more time for your work.
Thank you.
Thank you very much, Milton. So now, Augusto.
Yeah. So yeah, thanks a lot for the invitation, for giving the chance to read the manuscript. Congratulations on the work. It's very nice. I do share a bit of the concerns from Milton. I was missing some. So, for example, in the beginning, you explain a bit the background of the literature. It's very fast, and it's mainly words and citations like C 7, 8, 9, 10, 11, 13, 25. And I think this is an opportunity you have to look for opportunities to spread your big block of definitions. So, for example, if there are some things you can define earlier to explain in more detail what people have done before, now you have a definition that's surrounded by context. So you have to look for these ways to spread your definitions from one single block to something more motivating, more easy to read. Another warning sign is when your definition is not used right after. It's probably a sign that it could have come later. It's very tempting when you understand everything and you want to write to just say, okay, let's get rid of all the definitions and then lemmas and theorems. But if one lemma could come in the middle of the block of definitions, that's already another chance to spread and give the reader an opportunity to exercise the definition and fixate it. Also, the pictures are very well done, but they are usually delayed too much. So the figure 1 is very helpful, but you start to feel like you need a picture 3-4 pages before it comes. And then at some point you see, see figure, okay, so that would be a figures. Then you go 3 pages and then you see the figure and everything makes sense. So it could have come before. Especially bad for figure 3, because it's something like 20 pages before I already missed it. So it's very delayed. It's not a problem if you put a figure that the person cannot understand everything. Very early on, you put a figure and there are some indices or some things written to the figure that the person cannot understand, if it's explained in the caption. If in the caption you say, this figure explains this, which is happening right now, and you can also see what's in lemma 2.24, 2.46, then the person says, okay, there's some stuff I'm not supposed to understand yet, but I already benefit from what I can understand. But yeah, these are all suggestions in terms of presentation to complement what Milton said. I agree with him that the nice math is sometimes too delayed or too hidden. All that said, some questions for out of curiosity, really, or for what you plan to do further in this investigation. First is, I was very positively surprised that you understand what happens at the top of a local maximum, even if your starting point is at a local maximum. I thought you were going to cut. When I started reading the thesis, I said, okay, you're going to cut the local maximum because that's too complicated. Let's get the starting point in the basin of attraction. But then you managed to understand what happens starting at the maximum, which is nice. So I have a question. What happens if you don't have the second derivative negative there? If it's like a...
you mean if you have
if
like
B prime is not what negative? If B prime is 0, but then you have a fourth. Imagine that your local maximum looks like a minus x to the 4. Then I think you would need more, maybe some, I don't know if there would be log corrections or something. Because these derivatives appear everywhere, right? They appear in the stationary distribution. Everything will blow up, so I don't know what this blow up means in terms of the final result, if there will be log corrections or something.
Yeah.
Do you have an intuition?
No, apparently no. Actually, no.
Another question I have, I think the most interesting aspect of the thesis is breaking with the reversibility. And the fact that you are working on the torus, if you unwrap the torus, you get the line, and in the line everything is reversible. But another way to say this is that in the torus, if you localize to an interval, it's going to be reversible. Right? Every time you restrict your dynamics, like you said, you reflect, it's going to be reversible. So what happens if you have a system? Do you think your techniques could be extended to a system that is in high dimension, but every point has a neighborhood that is reversible?
Yeah, so you have some kind of local reversibility, but you're in higher dimensions. The techniques regarding the asymptotics of the rate function, do you mean, or which one?
Starting with just the Markov dynamics.
For the Markov. I mean, you could have some, I believe that you could have some dynamics up to a certain point in that locality, right? Because if it is reversible locally, you could have a way to actually compute how is it that you escape from attractors over there. And so you could have some asymptotics regarding jumps there, but Regarding the diffusion, I think that you could, actually. Regarding the rate function, I don't know. I don't know, but regarding the diffusion, I think that you could.
Okay, all the other questions already asked. All the questions I had, so congratulations again. Thank you.
Thanks.
Thank you very much, Augusto. So, Hubert, I've seen that you have many questions.
Yeah, no, I wanted to ask Augusto's question, so I won't ask it again. So he stole my best question, so I will go for the last good ones. So I have a question about your figure, the one on I think it's page 27, figure 1, like it's on slide 28, I think. Okay, and there was something that perturbed me in this figure, is that okay, I saw that on level 3, okay, the red level.
Yep.
Okay, that from you know, like this m-2 here, it would also have the possibility to go to the left. So is it that there is something that I'm not understanding, or you didn't want to go out of the picture, or?
I wasn't considering what happens on the left, actually.
Okay. So the what's this peak here? It's not okay. I was thinking the picture was periodic, and that this sigma -2 and this sigma 5, they were the same thing. No, okay.
Yeah.
Okay, so this and yeah, another question about the theorem that appears on page 35.
Which one?
35. Okay, so I couldn't exactly follow how you define your wells, but so I imagine that the answer depends on how these EP are defined. But do you have something interesting to say about this rate of convergence here to 0?
No.
Okay. Okay, so these were the questions. Perhaps I can do a bit of comments about the presentation. So I mean, I didn't have time to get very deep into the thesis, so I liked the presentation quite much. It was somehow self-contained. One comment I could do is that it was really fast-paced. So I think the reason is probably because the subject is technical. You need lots of definition. But I think perhaps an advice for future presentation, you have to try to find a way to simplify a couple of things in order to reduce the content. When you have if you have to summarize things in I mean, sometimes you will have to do even shorter talks, and I think for people that are not familiar with the subject, it will be very hard to enter in it because it's going fast. So it's I mean, I have no suggestion on how to do this, because this require basically you have to cut things off, and it's really difficult to choose where to do the cuts. But and I understand that it's more difficult when the subject is technical. But this is the comment I could do about the presentation. Okay, so, and well, thank you very much for this invitation to be part of this journey.
Thank you.
Thank you very much, Hubert. So I think now that the audience will leave the room, and the committee will now meet this side. So Christian, the committee appreciate a lot your work and is very happy to give you the title of Doctor of IMPA. So congratulations. Okay, so thank you again for participating.
Thank you.
And
you.
please send your comments. Thank you. Bye.
Bye-bye. Congratulations again, Christian.